Dear students, in previous class we were discussing about the uniform continuity of a function, and we say that if f and g are any two uniform continuous functions, then f plus g is uniformly continuous, f composition g is also uniformly continuous. Moreover, f into g is uniformly continuous if both are bounded. If both the f and g are bounded. F and g are bounded. So, now in this class, let us discuss about the uniform continuity of a reciprocal of a function. That is, when f is uniformly continuous on A, and f is unbounded, that is modulus of f of x greater than or equal some k where k greater than 0, then 1 by f is uniformly continuous on A, where A is a part of R and f is a function defined from A to R. So f is uniformly continuous on R. For the uniform continuity of the product of two uniform continuous function, we use the idea that f and g are uniformly continuous, then their product f into g is uniformly continuous only if both f and g are bounded. But here, mod f is uniformly continuous on A and mod f of x greater than or equals k where k is a positive real means f is unbounded. When f is unbounded and f is uniformly continuous, then we have to show this 1 by f is uniformly continuous. So how to prove this one? 1 by f is uniformly continuous. So in order to prove 1 by f is uniformly continuous, we consider modulus of 1 by f of x minus 1 by f of y, provided modulus of x minus y less than delta. If modulus of x minus y less than delta, then consider modulus of 1 by f of x minus 1 by f of y equals, it is modulus of f of y minus f of x, since that is nothing but it is f of x minus f of y divided by modulus of f of x into modulus of f of y. It is modulus of f of x minus f of y by f of x into f of y. That is modulus of f of x minus f of y by mod f of x into mod f of y. But what is f? We know that f is uniformly continuous on A. F is uniformly continuous on A means, that is, if mod x minus y less than delta, then modulus of f of x minus f of y strictly less than epsilon for all x comma y for A. Okay, where epsilon and delta are positive. Epsilon greater than 0, delta also greater than 0. So it is modulus of f of x minus. Moreover, we know that modulus of f of x greater than or equals k for all x fallen A. Agreed. So that implies 1 by mod f of x less than or equals 1 by k. Similarly, 1 by modulus of f of y, which is also less than or equals 1 by k. Why? Because y is chosen again from where? A itself. Okay. Therefore, this should become 1 by modulus of 1 by f of x minus 1 by f of y is numerator, it is less than or equals, sorry, it is strictly less than epsilon. Okay, suppose it is k square into epsilon. It is, since k is positive, suppose it is k square into epsilon. So it is numerator is k square into epsilon divided by, what is the denominator? It is less than or equals k square. So it is equals k square and k square cancelling each other. What means that it is epsilon itself. So means if modulus of x minus y less than delta, Then modulus of 1 by f of x minus 1 by f of y strictly less than epsilon That means 1 by f is uniformly continuous on E. Agreed? So this is the proof. Enough. Now we are going to another important result. That is, suppose f is uniformly continuous on a bounded set. Now we are going to another result. If f is uniformly continuous on a bounded set, of A. Suppose A is bounded set A, which is a subset of A. Okay. Then f is bounded on A. Then f is bounded on E. That is, when A is bounded, and f is uniformly continuous, then f is bounded on E. If f is uniformly continuous on E, where A is a bounded subset of R, then f is bounded on E. How do you prove this one? So the proof is, it is given A is a part of R, A is bounded. A is bounded. And f is uniformly continuous. F is uniformly continuous on E. F is uniformly continuous on A means, if modulus of x minus y less than delta, then modulus of f of x minus f of y strictly less than epsilon for all delta and epsilon are positive, greater than 0. Okay. A is bounded. So mark it as, consider this one. If x minus y less than delta, then modulus of f of x minus f of y strictly less than epsilon. A is bounded. A is bounded means it is, this A is covered by finitely many balls of radius some delta. A is bounded by the definition of boundedness. That implies A is covered. A is covered by finitely many balls. Finitely many balls of radius delta. That is, there exists some n fallen, there exists a natural number n such that A is a part of for n fallen, suppose n fallen n, such that A is a part of union I ranges from 1 to n open ball xi delta, where I ranges from 1 to n. Since A is bounded, so A is covered by finitely many balls of radius delta. That means A is a part of union I ranges from 1 to n ball xi delta, where n is a natural. And each xi fallen where? Each xi fallen A itself. Okay. Now we define. We define f of, or small m equals minimum of f of x. Minimum of f of xi, where I ranges from 1 to n. And capital M equals maximum of f of xi, where I ranges from 1 to n. Means since then let f of x has both the minimum and the maximum value, let m is minimum f of xi and capital M is maximum f of xi. Let x fallen A is arbitrary. Suppose x fallen A and A is covered with a ball of xi delta. So that means, so we can find an xj, there exists a xj fallen A such that this x fallen ball xj delta. X fallen where? X fallen A. That is arbitrary. So x fallen union of these balls. Means you can find out an xj fall in A with each xi fall in A. So xj fall in A such that x fall in one of this ball xj delta. X fall in one of ball xj delta means modulus of x minus xj strictly less than delta. So when mod x minus y is strictly less than delta, this condition holds. So when mod x minus xj is strictly less than delta, that means modulus of f of x minus f of xj strictly less than epsilon by using this argument. Okay. But what is m is minimum value of f of xi? M is minimum value of f of xi means what is f of xj? F of xj greater than or equals m. F of xj greater than or equals m for all j, that means f of x greater than or equals some m minus epsilon. Again, since capital M is maximum of f of xi, capital M is maximum of f of xi, this should imply f of xj less than or equals capital M. That means f of x less than or equals capital M plus epsilon. Okay, so that means combines these two arguments, that is f of xj or this one f of x greater than or equals m minus epsilon and f of x less than or equals m minus epsilon. That means this for all x fall in A, f of x fall in closed interval m minus epsilon and m plus epsilon. So that means f is bounded on A. Okay. So when A is a bounded set, f is uniformly continuous on A, then f is bounded on A.